Hey guys, this is Dr. Aeronautics, and we are going to fly this thing here to the moon, and we're going to come down onto it with a soft touchdown. Check out my channel because there's something very important that you guys need to see. Open up my previous video, Orbiter 2016 Tutorials 13 - Flying to the Moon Part 1. Fast forward to time 5822, and there you'll see all my math equations that we put together in the previous video. Unless you want to see me pulling numbers out of thin air, you might want to reference this document. I build the document on the video, so if you want to do that, you can build a copy yourself and see how these equations actually work. But I'm going to be referring to this document often. So I have a working copy that looks exactly the same as it did last time, and that's how we're going to fly to the moon. So without any further wasting of time, let's start our 250,000-mile journey. As a proof of concept, I've set the time to now, and the orbiter is off. What we're going to do is we're going to see when the next opportunity is. This video is being recorded at the UTC displayed at the upper right hand corner. We're going to get ahead because we need to do some time compression. But anyhow, the first step is to determine your launch opportunity. So we're going to calculate the takeoff time in on the math equation spreadsheet. This is going to be column G, row 49. We're going to calculate the takeoff time. Okay, so what we're going to do is we're going to target moon, and I won't go through explicitly every single step because it basically comes naturally to me, and I want it to demonstrate coming naturally. So this line here represents the moon's orbit, but again, we don't do it like this because it's showing a ground track, which really isn't helpful. What you really want is orbit plane. That will reveal the moon. And as things should turn out, we actually can't launch right now. We're going to have to wait until a considerable amount of time. Okay, good. The joystick is working. So what we need to do is we need to wait for the highest, approximately the highest point of the orbit to swing around. So I don't think if I do track, yeah, it won't tell me precisely where I am. So I'm going to have to get a good handle on precisely where we are. So if I zoom in all the way to 128 and I line up precisely with that line and move this over, now would be a good opportunity to take in my current latitude. So okay, so it's exactly half of a screen on 128. So right now I'm going to fill in F51. Your nodal crossing latitude, it's going to be negative 80.68. Now we need to find the moon's nodal crossing latitude. So we're going to zoom all the way out again, and we're going to move over now. And what we're going to do is we're going to find out specifically when, so we're going to need to do a relative inclination adjustment. Remember I said that there was the instance of needing to do that. In this case, we're not going to be able to get away without a relative inclination change because unfortunately, Cape Canaveral is north of the Tropic of Cancer, which means that we are not going to be able to do straight onto the moon. We're going to have to do a relative inclination adjustment if we want to make this simple, which is exactly what we want to do. Okay, so now I need to figure out which longitude this is here. So this is approximately in China. Yeah, southeastern China. So what I'm going to do now is I'm going to open up one of my very happy weather apps and use it to determine precisely where this is. It's probably going to be right around 120, 115 to 120 for longitude. Okay, so let's see. Looks like we are right now. Looks like we're under Chantal. I think that's about right. So it's 116.7. Okay? So I'm going to go back to my calculations, and in F50, I'm going to enter 116.7. And that is where it will be most fuel efficient to fly to the moon, because we'll be rotated underneath the path of the moon. Almost, but not quite. Okay. And so what we find is the launch time is about 13 hours, 0.158 hours away. So if I do a quick calculation real quick, 0.15867, and it changes with every minute, times 60. So we're going to find exactly 13 hours and 9 minutes, 30 seconds. Now, because of the 9 minutes and 30 seconds, is the time that it takes us to get to orbit, and because you want the time that you cross the nodal point when you reach your injection point, we won't add that 9 minutes because it's going to be spent ascending. So 13 hours and about 11 minutes, minus 11 minutes is what it takes to get to orbit, leaves us with 13 hours even, which means we've now discovered our launch time. Write it down. It's going to be 23:35:00 plus 13 hours even. So that's going to be in UTC. It's going to be September 14th at 12:35:00 UTC. And that's when I'm recording, that's going to be just about 12 hours from, just about 13 hours from now. But unfortunately, we can't do that because we're going to have to time warp. We can't wait 12 hours. So I'm going to time warp to launch time, and then we'll keep going from there. Okay, it is the next morning. You might as well say that we spent the night in the ship. Because we basically went from sundown to sunup. And if you look, we're now in a pretty good situation. We're still about half an hour early, but we're going to start configuring the craft to take off now. So we're going to launch, we're going to do an orbit injection, we're going to do a plane change. So I think now would be a good time to power on the second MFD. We'll go to align planes, and we're going to target celestial bodies, pick moon. And now you can see there's 8 degrees of relative inclination. It'll get a little bit lower, but we're still going to have to deal with relative inclination. You notice I still have all of my propellant because I want to do this right. I want to do the ascent right, and I want to have plenty of fuel to fly the mission. Let's go back to surface. We're going to turn the HUD on, and I want red because it shows up better. We can leave our air flight control surfaces off now. There's no reason to activate them just yet. We're going to turn our landing lights on, and we're going to turn our strobe beacon and nav lights on. And now, with the exception of turning the air flight control surfaces on, we're basically ready for liftoff. Just as a quick note, one additional thing that you might want to do is also open up the spacecraft's cabin hatch, because in spacecraft that simulate oxygen consumption, such as the XR2 Raven Star, it's a really good idea to leave a hatch open. That way you're using the fresh oxygen atmosphere while you can, and you're not taking down on the time that you could spend on the oxygen, unless you want to do an oxygen dump, which, you know, I mean, there's a button for it. But anyway, so what I'm going to do now is continue wasting away our time. So now we'll go up to pretty much about 1 minute before launch. 1 minute to launch. And now you can see the lines have just about pretty much synced up, right? If I put it on track here, you can see these two lines are now as close together as they're going to get pretty much in about a minute. There's not anything more you can do about that. That's just the fact of the matter that we're just too far north of the equator. It's just not going to work. So let's go ahead and reset the track here and zoom in. We are to prepare for launch. Let's check our relative inclination here. So we have about 7.5 relative inclination degrees. So we're going to be doing that pretty soon. Oh, whoops. I almost forgot to calculate our azimuth. Well, we have 15 seconds to do it, right? The equatorial inclination of the moon is, it's actually below our, let's see, we need to go to frame, equatorial, projection, ship, target, celestial bodies, moon. Let's see, inclination is 20.91. That looks right. 20.91. That's in cell F54. And then in launch latitude is 28.6 degrees north. And in that was in F55. And the answer's in F56. You get an undefined number. When you get an undefined number, it means no matter what you do, you can't get into the inclination you want. The reason is because we are further north of the relative inclination that we want to reach in terms of latitude. So you remember I did this in a previous episode. There is nothing we can do. So which direction do you launch? Due east, 90 degrees. Pitch air flight control surfaces on. Going to add a little bit of elevator trim. The lines have synced up. This is as close as we're going to get to the moon. So we are going to turn due east, and we're going to hold this inclination that we have now from the rotating Earth. So let's give it a 3, 2, 1, full power. There's 100 meters per second. And 160 rotating. And there's a positive rate, so we're going to put the gear up, and immediately, to conserve everything, we are turning to 90 degrees. Retracted. Also, I'm going to throw the throttle down so that we don't waste anything. So I'm going to waste absolutely no time in this turn. We're going to go very quickly to 90 degrees, and once we reach it, we're going to hit the throttle again. Again, you don't want the little airplane symbol, you want the cross. The cross is the prograde velocity vector. Let's see where we are. Yep, just about 1 degree off. Okay, full power, pitch up to 30 degrees. So even though I say 86, that's okay, because we want the cross at 90, and the cross right now is exactly at 90. So just keep the wings level, and everything will be good. Once you're at 30 degrees, you don't have to worry about much. The ship will basically fly itself. Again, just let it drop. It's going to drop to 20 and then 10. You don't want it to go below 10. Just passing through 20,000 feet. And we've just hit Mach 1. That was a little bit unrealistic, by the way, because relative speeds, you can't really hear that from the perspective being still. But anyway, that's too much physics. Okay, I see another destination in sight. Given how close it is to the sun, I'm going to bet it's Mercury. Press F9, we can cheat, and it is indeed Mercury. (40,000 feet in altitude. Okay. We don't want to be any lower than about 15 degrees here, so I'm just going to continue adding up elevator trim. The idea is about once a kilometer you drop you drop a degree. So when you're at the surface, you're at 30, and when you're about 20 kilometers, you're basically at 10. And once you reach 10, you just want to continue at 10. Okay, we're coming up on 10. So once we hit 10, we're going to begin adding more elevator up trim to prevent us from going below it. (80,000 feet in altitude, speed now 1 kilometer per second. You see how I'm trying to match this up almost perfectly? Now, once you pass through about 100,000 feet, which is 30 kilometers, stop trying to hit 90 degrees, because at that point you'll be running you need to run a great circle. So what that means is allow yourself to move southwards, because lines of latitude are circles, they're not straight lines. And there is 30 kilometers, 100,000 feet. Everything looks good. Just keep an eye for plasma. You don't want plasma developing at the nose. Check your fuel. Okay, we're doing good. We still got 16,000 meters per second delta V, which should be plenty. We might not even have to refuel on the moon if we want to come back. Keep the wings level, and make sure that you're continuing an upward track. Okay, I've got plasma, so we're going to go full elevator trim now. Keep an eye on that dynamic pressure. That's going up, so now I'm going to begin adding the stick. At this point, it would be a good idea to switch to your aligned planes, and what you want to look at is under relative, you want to look at rate, and if you see a positive rate, that's bad. You don't want a positive rate, because that means that you're adding more fuel that you'll have to expend later. So just make sure that that's negative or 0, not positive. Okay, so that's just gone positive again. So in our case, negative means more left turns, but not too many, because then it'll go the other direction. Okay, so we're at 45 kilometers now, which is a good altitude for us to be at. So we can actually level out. At this point, it'd be okay. Okay, we've gone positive again. So increase that bank angle to where you go negative. That's what you want. There we go. That's looking really good. So that'll also adjust your descending and ascending nodes, and when they're halfway in between, you know you're doing what you should. Also keep an eye on your lift vector, because we do only have about 3 kilometers per second. We're at 48, so we don't want to really go much lower. In fact, we want to go higher because I see plasma again. So I'm going to pitch the craft up to about 10, and so our vertical speed gets about to 250 to 300 meters per second. And once it does, we'll be fine again. Okay, so if you look at the relative inclination chart now, we're basically swinging the descending and ascending nodes. When that happens, turn your wings level, because then you're beginning to go on the other side. So we're essentially flying right down the middle of an inclination line is what's going on. Let's see, we're at 52 kilometers. That's a good place to be now. Oh wow, I must have left the stream. I see we had basically hardly any acceleration earlier. It was kind of bad. Bad waste of fuel. Okay, so now being halfway between our descending and ascending nodes, I'm going to completely level the wings now and keep them level. And this will ensure that we have the least amount of fuel possible. We're still going to need to do a long inclination burn, but at least it won't be mission destructive. So in Apollo, they skipped this and went for harder math. I think the Russian approach was to do an inclination adjustment maneuver, but it is what it is. So in order to keep the math easy so that we can actually do it and figure out, like with budgets and whatnot, I'm going to do an inclination adjustment as a separate maneuver. That way we can actually tabulate it and keep track of our delta V usage. Okay, 4.8 kilometers per second. We're about 60 kilometers. We don't want to go further down, so I'm just going to keep pitching up again. So I'm taking note, the relative there it goes. Relative inclination is 7.64, and that's the number that we want to have. There's no reason why we're going to lose 7.64 except with my own idiocy. So keep an eye on that number, and if you don't see 7.64, do what you need to during the ascent to get back to it. In my case. Oh, there's 7.65, which we don't need. Okay, back to 7.64. So that's the number that I'm going to continue beating until we go into, okay, now if you get a lower number, that's even better. So now I'm going to keep 7.63. 5.7 meters per second, we got it, or kilometers per second, we have about 2,000 meters per second to go to orbit. So I'm going to tip the wings a little bit left because we want to, the craft seems to want to move right. And see, here's what I'm talking about again, you know, we're almost at 100 degrees, but that's expected because we're doing the swing here. If I go to the map, you can see we're swinging southwards. That is intentional. See how our orbit's developing. That's looking pretty good. So we're at 66 and ascending. Still got some plasma. 7.63. Everything looks good. 6.5 kilometers per second. Just about 1,200 meters per second to go. So I need to pick a parking orbit altitude now, and that's going to be, actually I can pick anything I want. So you know what, I'm going to pick 270 kilometers. We're going to change dist, and we're coming up on it now. So when I reach an apoapsis altitude of 270 kilometers, I'm going to shut my engines off. So have a relative inclination of 7.63, we're doing good. Okay, now 7 kilometers per second. Just about 700 to go. About 600 to go. And we're having the perigee-apogee swing around right now. Let's see, about 400 to go. Okay, there's 150, 170, 190, 217, 248. Okay, and that's it, 272. Main engine cutoff, we're now in orbit. Well, not quite. I mean, we're still going to be negative. We'll have to do a circularization burn. Okay, so what do you need to do now? There's a relative inclination burn that needs to happen. We're going to swing around to our descending node. So we need to decrease at the descending node, which means we're going to burn ascending, and the thrusting time is 66 seconds. So we're going to use the engines for 66 seconds in order to kill off this relative inclination. Okay, so we're going to switch over to orbit for our MFD now. I'm going to go green because I'm in space now.
Rotation.
Turning on rotation, turning the useless air flight control surfaces off, but before I do that, we're going to reset the elevator trim so that we don't have a bias. That won't matter on an airless moon, but if you go somewhere like Mars, you can get in trouble. Okay, air flight control surfaces are off. We're going to turn prograde at this time. Check our static pressure and our dynamic pressure, and both of those are very low. We're up above 94 kilometers now. So at this time, I'm going to put the landing gear down, really extend the radiator. Oh my god. Oh, I cannot believe it. Well, we broke the hatch. Don't make the same mistake I did. I'm turning the landing lights on. Okay, this room right here is vacuum. There is now no air inside the spacecraft, and basically, if you take your spacecraft off now, you're gonna, or the space suit off, you're gonna die. The good news is when you get to more advanced things like the XR2 and the DeltaGlider 4, there will be visible and audible warnings when you do something like that. So everything's okay. I'm going to cheat the door back. Alright guys, everything's cool. I did a damage abort using Notepad++. You can fix anything with Notepad++. So yeah. Let me just tell you that designing a spacecraft with any sort of warning advice that you have a door open is a really idea. And to be honest, I would notice that when we start going 1,000 miles per hour in the atmosphere. I would start noticing things flying around the cockpit. So when something like that happens, I get anger issues and will cheat and do anything else that I need to do in order to restore the state that should very well be. Let me tell you, if I had ignored a warning, that would be completely different. If I got a warning and I ignored it, no, now at that point it's my fault. Or if the warning failed. But as long as the master warning system tests okay, that's like cheating. Okay, so we're going to go to about 2 minutes before the descending node. Right now we're about 770 seconds from it. Okay, we're about 2 minutes before ignition. Isn't this just the most beautiful oceanscape? It makes me even happier to see it now, because I'm going to be playing Silent Hunter 4 this weekend. So it's extremely appropriate. I don't know exactly where we're over right now. Oh, it's over Africa. This is the one spot in the ocean where I won't be. Wait a minute. Yeah, that's us. Okay. Alright, let's go back to align planes, and we're going to prepare for this maneuver. Remember, this is a descending node, and we want to lower, which means we burn opposite the direction that we're going. Which means we go in the plus direction. We're going to be using our main engines to do this burn. and it's going to be 67 seconds long. And we're going to have ignition when TN is about 33.48 or 446. Yeah, 46. Need to divide by 2. I think that's Gabon down there. I think so. There's areas of the Earth where my geography needs to get better. Okay, while we're waiting, let's take a look at our propellant status. So we've got 4,500 kilograms left in the tank, so we've actually gone through more than half of our fuel. That's not too concerning. Perhaps I should have used some of my scram fuel because now it's just sitting there along for the ride. But hey, I mean, you live and learn. So we can pull up to 9.7 kilometers, or yeah, 9.7 kilometers per second, which is just fine. So we're going to have enough fuel to fly the mission. We're just about 33 seconds from the burn, so we'll start getting ready for that. The next thing we'll have to do is circularize our burn. And yes, I know translunar injection sounds like a long way off, but it's coming. Okay, get ready. And 5, 4, 3, there we go. Okay, so relative inclination's counting down now. If I take a look at the map, you'll see that us and the moon, this got deselected when I did my damage abort, and also changed this. There we go. You can see these two lines are now converging, so notice a pattern. This is exactly what we did with the ISS and exactly what we did with Mir. Now thank goodness that it's not going to be a significant burn, because that would be really bad. Go back to aligned planes, we're probably getting really close. Keep an eye on that fuel. Look at you can just see how expensive this is. So notice how our speed doesn't change, but we're still expending delta V like crazy. That's a really good indicator of how horrible it is for you. Okay, that's it. A relative inclination of 0.02 is plenty fine. We're targeting a celestial body, not a space station. So it's a lot larger. In fact, we can see the moon. If we were trying to get to the ISS, we couldn't see the ISS where we are now. Now, that's not the case when you're going to a planet. I know what you guys who are veterans are thinking. Yes, if I want to go to whatever this thing is, I can't get away with 0.02 degrees relative inclination. I'm going to go hundreds of thousands of miles above it and completely miss it. But for something as nearby as the moon, it's actually a really easy target to hit. We now have our relative inclination synced, which means the next thing we need to do is circularize our orbit. And notice, we completely underlay the moon. That is exactly what we want to see. Turning prograde. And we have apoapsis in just about, let me see, just about 7.5 minutes. So we will be doing that next. Okay, we're getting really close to apogee. So, concept check. Knowing that we orbit with our plane as the zero pitch, where is the moon going to appear when we see it in the sky? Because we have our relative inclination synced up, the moon will appear out our right window, completely level with us because we've synced up our plane with its. Okay, we'll hit the engines now and we're going to circularize. Getting close. Okay, that is pretty much circularized, so we're fully in orbit now. I'm going to go ahead and... wow. Our prograde autopilot wasn't enabled, but that's okay because we added a little bit of outward. Outward isn't going to hurt anything except rotate the apsid node, which is extremely low at this point, and we don't have any pitch, which is the really important thing. So let's see if we can actually find the moon, because we want to make sure we have a place to go. Whatever. We'll worry about that later. So, that is it. So here's where things change. We're going to calculate the translunar injection. This is something we've never done before. So you're going to go to the transfer MFD. You're going to choose reference as your planet, which is Earth. That's already selected. Your source. I think you need to do by name. Yeah, self. So that's the orbit that we're in now. That's what you need for source. If you wanted to be like Invader Zim and move Mercury to Mars, then you could select Mercury. And we're going to choose target, go to down celestial bodies and choose moon. Okay, so now you'll see an inner circle that's green and an outer circle which is gold. The green circle represents our orbit around the surface of the Earth. And the gold circle represents the circle around the circle that is the moon's orbit around the Earth. And if you'll notice, there's a gold line and a green line which are really close to meeting right now. And that's good. The gold line is the position of the moon through its orbit, and the green line is the position of us through its orbit. So that means that the moon was actually right here all along. So the question is, where is it? Well, it must be a new moon because I can't see it. So let's go ahead and cheat with F9. Aha, there it is. Yep, it's a new moon. It's really hard to see, but that's it. Okay, so what this means is the translunar injection is going to take place on the other side of the moon. That also might cause a problem because, yeah, the far side, the near side is going to be dark, which means we're going to be landing at night, which really sucks for tutorials. But anyway, okay, so what you're going to do is you're going to hit HTO. That sets up this thing known as the Hypothetical Transfer Orbit. So let's go Hypothetical in the clavicle and hold down the DV plus button. So what that says is, in a hypothetical orbit, at this time, right now, as I'm planning this, we're going to do 5 meters per second. No, 15 meters per second. Look at this DV here at the very bottom. That's what you want. And this orbit is changing. It's calculating a change. So why did it move? Because we only move 15 meters per second. Let's try 2,000 for DV. You're going to hold down that button for a long time. You watch that green circle turn into an oval, and it will begin stretching out. There's one. And there's 2, and hey, now you might be able to actually see it. Right? That dotted green line. Should be showing you like sync orbit. Okay, we're getting close. Oh, there we go. Okay. So there's this gray line, and this gray line represents where you're going to cross the moon's orbit. So this is where you want the moon when you approach the moon. Or, yeah, when you approach the moon's orbit, this is where you want the moon. So what we're going to do, if we burn now, you now see a green dotted line, and the green dotted line tells you where to burn. The yellow or gold dotted line tells you where the moon will be when you reach this gray point here at the intersection. So as you notice, we're 90 degrees apart. So there's a really big issue. It means when we're here, the moon will have moved from here to here, which is what we should expect because it takes about 3 days to fly to the moon, and the moon orbits in about 30 days. So we should expect about 1/10 of a pie slice taken out. So what can we do about this? Do we have to wait for the moon to come all the way around to here? No, because we're orbiting the Earth at a very low altitude. When the Earth orbits the sun, you want to go to a planet, you're going to have an issue, because then you'd have to wait 6 months to get to the other side. But how long is our orbit around the Earth? Just about 88 minutes. So as a result, all we got to do is just move the burn by about 45 minutes. So you press this EJ minus and EJ plus, and it's going to adjust when you do your ejection. So if I do EJ minus, and I go all the way to where the green line meets the green dotted line, it basically means we're going to burn now. So here's 4, 3, 2, 1, and boom, right there. We just hit when we should have burned. But because the moon is over here, in reality we're about 40 minutes from where we should actually be burning. So we're going to hold down this EJ plus button until this swings around. And simply put, in about 40 minutes, this green line will be at the green dotted line. And that's where our math is going to begin to come in. Okay, so remember, don't line up the gold solid line with the gray solid line, because that's where the moon is now. You need to line up the gray line with the gold dotted line. Okay, and now you know what's happened is our intersection just broke. That's because the moon doesn't orbit in a perfect circle. So we need to add a little bit more gas here, and we're going to adjust our right there. So you get close, begin seeing how much you can cheat on this because it's really wasteful. And right about there, we just about got it. So you can't get any real closer than this. And that's where we're going to be. So look up from DTI and TLI. You have this DV. What is this DV value? That's the delta V value. So go down to F60 in calculate burn time of TLI, and you're going to see 3121. It's going to be a little bit off. 3124. Now you see why I picked the 3121. Okay, spacecraft mass. Scroll down here, and yeah, can we actually get a mass estimate from this? I don't know that we can. Okay, well, I don't think it's cheating that seriously. In real life, you would have to keep track of this with a spreadsheet, and you subtract out how much mass you burn based on how long your engine is on and at what throttle setting. So you press F4, go to Info. It'll come up with focus vessel, and it comes up with U. Right now I have a mass of 20,267.9. So I'm off by only about 800 kilograms. Not bad. 2267.9. The closer I am with my estimations, the more sane that I think I was at the time. And the more I trust myself. Thruster main group, it's not 320 or 340, it's actually 320,000. So enter the mass in F59 and enter the main engine thrust in F58. 320,000. That won't change. That's a constant. So this burn is going to be over 3 minutes long. It's going to take 198 seconds. But remember, you're accelerating. So now this DTE right here, which is now reading 3020, that is when you're at the point of translunar injection. It is not when you need to begin your engines. This MFD assumes a perfect, absolute impulsive maneuver, which means you're going slow, you're going at 7.7 kilometers per second, 7.7 kilometers per second, bang, 10.2 kilometers per second, like you're shooting a gun out within an instant. You're going that fast. We can't do that. So we have to factor in the fact that we're going to need to accelerate. And what happens when you accelerate? That's a v squared. And if you drop the term, v is the squared of in calculus world. It's the what is it? It's the integral of distance over time. So you drop that number and then you get 2. So you have to divide in order to get distance. So even though it says time to burn 198, half of that time is going to be on the front end and half of that is going to be on the back end. Because whatever you do on the front end is going to change before you get the back end. So, okay, that might sound a little bit confusing, but basically imagine adding the sand on the right side of the container for half of the time and then on the left side of the container for half of the time. That's basically what you're doing. You don't add all the sand on the right side, because that would mean we would start at 198 seconds and then we're done. You need to, as you move from right to left, you need to burn the whole way. So we're going to do our translunar injection at not 198, but 198 over 2, which is 99. So when DTE is 99, that's when we burn. So we're going to go forward till about 2 minutes before that time. Okay. Not much time has passed. Let's see where we're over right now. Looks pretty close to sunrise. We got to be pretty close to Florida. Oh no, I forgot about an hour and a half went by. So let's see, we're actually over Baja California right now, just south of it. Down here should be the Galapagos Islands, and that's going to be South America. No, that's going to be Mexico. I believe down here would be Oaxaca. Somewhere around here. Oh, come on. You can't tell me that Oaxaca's not on the map. I think it's just hidden because it's a little bit, we're not far south enough. Okay. So, we're now 235 seconds from go time. So we did build up another relative inclination, and that's big enough that we're going to need to adjust it. But here's the cool thing. We're going to swing all the way out here and look at where our node is. Because we're going to be burning level with the horizon, we're going to be way out here where the intersection of this gold line is with this dotted green line, which means we're going to be going slower, and a plane adjust for 0.14, just probably a few taps of the translation thrusters. Okay, we're under a minute to burn, and there is no indicator on here that tells you when to burn, so you need to watch that time or you're going to get it. Turning prograde. Okay, I remember Guadalajara. I was over that for one of my Norsdenland episodes. Okay, and you should take your TLI very seriously because it's a big burn and it's very unforgiving. So I'm going to give multiple call-outs for this. So we're at 99. 49 is going to be at minus 50. Minus 50. Minus 40. Come on, where's Oaxaca? Guatemala? It's not on here. Well, Oaxaca should be somewhere down here. That's dumb. I want to put it on the map. My favorite place in Mexico. Okay. Alright. Minus 20. Get ready on that switch. Oop, I hit it. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. TLI has begun. So we're going to get a pretty nice view of Africa and India on our way out. And that's based on my knowledge of our current geometry. You notice our DV value counting down? We have about 2.3 kilometers per second to go. This is a long burn. Make sure that Pro G is still selected. Okay, just about half done. Keep an eye on the fuel. We're now down to 3,000 kilograms. Still doing okay. We're going to be pretty close to running out. We're not going to be able to come back to the Earth without a refuel. Okay, 1,000 meters per second remaining. And now you can see our orbit is starting to come out on the transfer MFD. And any minute now, our altitude is going to start going haywire. Look at how far we're coming out here. 400 left. We're also getting really close to escape velocity. Escape velocity for the Earth is about 11 kilometers per second from orbital altitudes. Okay, 200 left. 130. 96, 79, 62, 44, 27. And... ooh, just a little bit more, just a little bit more. Okay, almost. 0. That is it. Okay, so you have a perfect translunar injection right there. I can't even see the dotted line right now. And because the dotted line has become us, we've made a very good translunar injection. I'm very happy about that. This is the part where mission control calls back and they say, your orbit is just beautiful. Okay, so that is finished. Turn off HTO. You're done. So this is our orbit now. We're going to swing all the way away from the Earth. Select back to map. Track. Go to display. We're going to go back to ground track. And now we're going to watch some fun. So it's Africa that we're going to see. Disable Pro G. And now we're pretty much going to go into a deep freeze. So that is the last time we're going to see Cape Canaveral for a while, because we're going to go so far away from the Earth that the only things we'll be able to see are continents and oceans. And it looks like our altitude is already very high. Yeah, it's already about 430 kilometers. So next comes a inclination adjustment. And so I'm actually going to switch this back to orbit plane. Actually, that's no help. Let's just leave that on ground track. Go to align planes over here. So we'll need to... Well, even though we have a relative inclination, our ascending node is going to be really close to the point of the moon. That's what Apollo did. They actually matched one of their nodes with the moon. If you're really good at matching where your nodes are, then you can actually get it to where you don't need to do a adjustment at all. But that requires a lot more advanced math. So that's pretty much it. We're pretty much in a coast phase now for quite some time, because we can't do our inclination adjustment until we reach this node, which is a long way away. So let me see. If we need to do it, we'll be doing a mid-course correction maneuver next. But as of now, I really don't see a need to do it, because we just nailed it that good. This is what happens when you plan ahead of time. You can just really take the fruits of your labor. Okay, but we still have 5.5 kilometers per second of delta V left, which is perfectly fine. So let's take a look at the Caribbean as we leave the planet. Quick save, 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 save. Let's check to make sure our radiator's out. Good. And now that we're about 700 kilometers, there's no one up here. I'm going to turn off the rest of my lights. All right, let's enjoy us an Earth. Okay, we've just crossed 1,000 kilometers in altitude. The moon orbits at approximately 384. So we're starting from 0 and we're counting up to 384. Yeah, that's not really useful. Let's take a look at our map, show us what we'll be able to see. Okay, so Africa is going to be coming into view, and then up there should be the eastern United States. – 3,000 kilometers up now. To be honest, I think our translunar injection might be so good that our mid-course correction maneuver might be to avoid hitting the moon. Okay, so I want to point out something on the map. I don't know if I've mentioned it yet or not, but you know why we suddenly turn around? What is this? And then we fly around the Earth. So what's going on is, if you look at our speed, it's dropping. We're now at a 7.8 kilometers per second, and it's dropping, and it's going to continue dropping. So we're going out very far from the Earth. So what's going on is it's rotating under us, and we're actually going to be going out so far, it's going to be like a spinning top. So we're not going to be able to keep up with it, and it's going to keep rotating. Okay, 7.6 thousand kilometers. So we are now higher above the Earth than the center of the Earth is below its surface. And we're getting a great blue marble picture. Note that our apoapsis altitude, if the moon weren't there, would take us all the way out to 410,000 kilometers. moving up to 100 times acceleration. I'm going to change this dist to radius now, because I'm more familiar with radius where we are. And now you can see the dynamics are changing. This is the point now where we now move across the Earth slower than it rotates. And the Earth will now outpace us and begin rotating in front of our eyes. Okay, I want to stop right here because we're at 42,164 kilometers. This is where the Geo Ring of Satellites is. All the geostationary satellites that move at the same speed that the Earth rotates are in a ring around the Earth at exactly this altitude right here. If you have a 20-inch monitor like I do, or it might be a little bit larger than that, 22, whatever it is, this is what the Earth would look like from that altitude, and it is absolutely beautiful. Let's go ahead and save again. Note this G value dropping. Again, this is the gravitational value not accounting for the speed of the Earth around the Sun. So if the Earth were not moving and the Sun were not moving, then the Earth would be accounting for 97% of the gravitational force. The other would be that giant star we call the Sun. Okay, enough yap. We're going to go forward now until there's something that really needs to get done. Here's 1,000 times. Now you can see the Earth rotating under us. And the Earth now has a phase, which is pretty cool as well. So on our left should be the moon coming up. There it is, right there. We're a long way from it, a long way. Let me see, we're now a third of the altitude that we need, which is going to be about 1/10 of the time. Okay, if the Earth and the Sun were both still, the Earth would now be accounting for only 70% of the gravity. But we remain bound to the Earth strongly because it moves around the Sun at such a high speed that the tidal forces are very low. So the Earth, the Sun, and somewhere up here should be the moon. Yep, right there, starting to get a little bit bigger. Alright, since we're getting close now, that map really doesn't have anything to do with, so I'm going to go back to transfer. We're going to keep an eye here. Okay. So, it looks like things have gotten off by just a little bit. So, we might need to do a mid-course correction maneuver here. So what we can do is we can stop and see if I can... This might not support the operation of mid-course corrections mid-flight, but we'll see. See, I want to do mine right here. Okay. Looks like we need just a little bit more gas. 19 meters per second delta V. That's not bad. That's a little bit worse than a NASA mid-course correction maneuver. So this is prograde. So we're going to turn around to face the front. Interesting. So the computer's getting a little bit confused because we're starting to get far out from the Earth. Once we get below this G value where it says 0.53, then all of our instruments are going to reference the sun. And that's a little bit incorrect because if you do the G equals M1, M2 over R squared, or no, it's G M1, M2 over R squared, the fact that we're moving around the sun flips the calculations a bit. So you can't really rely that much on this. All right, so we're going to add 19 meters per second now. Four, 3, 1, 0. And that was it. Turn off HTO, and we're perfect again. So that's our MCC1, and only, hopefully, which means next is going to be the base target burn. That's going to be something a little bit funky that I'm going to describe once it's time. So I'm going to disable the autopilot, quick save, and we'll keep moving forward again. That is the Okay, so remember what I said, everything went to reference the sun, but remember, even though the G value says 0.48, the fact that we're going around the sun at 28.7 kilometers per second, and we're 150 gigameters away from the sun, which is 1 AU, we can still reference the Earth, even though the instruments want to reference the sun. The more accurate one would be the Earth, and I'm actually going to force the HUD to be Earth, because Earth has a lot more to do than the moon does. Pretty soon, we should start getting gravitationally tugged by the moon itself. If I go to graph, Earth over to moon, yes, now the moon has got 2% of the gravity field. So 2% of the gravity that is acting on the DeltaGlider is caused by the moon itself. So what I'm actually going to do now is flip over. We know the orbit, we know the approach orbit's good. We know that we're about 55,000 kilometers from the moon. So I'm going to switch this over to moon now. And now we should be getting a pretty good approximation of our approach orbit. And if I flip this over to dist, now you can see it looks like we are indeed on in a collision course with the moon itself. So we'll just do a base transfer burn when we get closer. Okay, moon's starting to look pretty big now. It's actually about the same size as the Earth right now. Okay, we're getting pretty close. Keep an eye on this alt. Where you see altitude, that's how high we are above the moon. So you don't want to get that below about 30 before you do your base target burn. Okay, 25% of the gravity field is now from the moon. Holy cow. out, it's getting big. Okay. So I think here is probably where you want to do your base target burn. So this is going to be a manual process. We're not using any math to figure this one out. So right now we've got a relative inclination of 144 degrees, which is a free return. I'm going to switch over to the HUD so that we can see what our lunar situation is now. Let's identify our prograde velocity vector now. Perfect. So it's looking right at the moon. And what we need to do now is go find our base. So you're going to choose map, and to change the map to the moon, you're going to do ref, scroll down to Earth, arrow key, and enter at moon. We've got a base, and if a target, go to Spaceports, Brighton Beach. And it's a little bit far north. We're actually at a really bad location right now. So it's at about 41 north. So we need quite a bit more inclination here. So I'm going to swap over to orbit plane so that you can see our orbit track. I wonder why that's not displaying. That's strange. Well, I was hoping to solve this graphically. Okay. Well, our inclination is 144 degrees now, which is it's the equivalent of about 35, 36 degrees. We need more than that. So let's see which node we're closer to right here. Okay. So it looks like the nodes actually occur at the center of the moon, which could cause a problem. So, we need to solve this puzzle. So what we can do is we know we need more inclination. So I recommend that we burn outwards and up. Again, they don't do this in NASA. They do numerical solutions, which I could do as well. So let's go out about 90 and the 45. And see what we get. We want a lower inclination, even though this I said higher. So we should be getting something closer to about, let's go for 60. So let's go for a 120. And we should see this PEA decrease. Okay, so that's going up, which means we need to burn the other direction. And not nearly as much strength. So let's do this. Here we go. Let's just increase that orbit until it's off of the collapsed moon. This was the situation that I was talking about where you actually did have to prevent yourself from slamming into the Earth. And this is going to take quite a bit of fuel to do, because we really were that close to slamming into the Earth. The moon, unfortunately. And I say unfortunately because we had a really low eccentricity, which means it's really fuel efficient when you come in. But anyway, we're gonna come up to a node here, which is really good. Oh, that's why it's all funky. You don't want to target the moon. We can target something that we know its relative inclination. And then we should be able to get... Actually, can I target the Earth? Can I back target? Actually, that wouldn't do any good. Yeah, that's kind of useless. I normally use math here. Okay. So we should be good for now. We'll just keep cruising towards the moon. And if I see something I like, I'll let you know. If I see something I don't like, I'll also let you know. Let's go ahead and save this real quick. Yeah, it really does irritate me that we're not getting an orbit plane map here. I don't know why that is. It could be that it's not mapping hyperbolically because, I mean, this is another type of orbit that we haven't encountered in any of our... oh, thank goodness. It's come up. Okay. I really like this. So, this is a strange orbit that we haven't encountered yet. It's called a hyperbolic orbit. We're moving faster, and we will be moving faster than the moon's escape velocity. So that means that we're not going to actually be able to stay at the moon. That's why they call this free return trajectory, because I have a negative inclination, which implies that we're going to swing around the moon retrograde. The moon will be throwing us backwards, which is going to slow us down. And when you slow down in an Earth orbit, you collapse. And the collapsed Earth orbit will bring us back to the surface. So this is exactly what Apollo did, was a free return trajectory. Okay, so I'm going to wait for the node crossing here, and that's where we're going to perform our base target burn. And it's going to be big, unfortunately, because of the way things are right now. We're going to do about a 90... You know what? I think I want to do it now. So, right now, even though it's 42%, we've got three contenders right now. We've got the moon with 42%, the sun with 40%, and we've got the Earth with 18% of the gravity field right now. So, our autopilot commands will work for the moon now. So, we're going to turn normal plus for the moon. And now that the moon is the strongest gravitational attractor, any orbital adjustments we make will affect our orbit around the moon first and the Earth second. So I'm actually going to disable the autopilot because we're going to burn so fast that the node is actually going to turn in real time. Watch this. See how that moves? And let's see, we got 129, 130. Oh, shoot, that's going up. Hang on. Descending node. Yes. Because we're retrograde. Everything is flipped. Actually, wait a minute. Is that what I want? Let's see. If I'm orbiting the moon retrograde, it means that I'm going to be moving from right to left on the screen. And if I'm moving from right to left on the screen, why does it look like I'm moving from left to right? Weird. Okay, so I should be moving from right to left. Which means I need to do a high bit of negative. So we should go through 180 degrees of inclination. A quick check of the math will show this. Again, the proper thing to do would be to solve the patch conic when you're further out, and then use the aiming radius to target the specific approach aiming vector for the moon. All right, let's take a look and see what that... Oh yeah, this is the direction to go. I was right the first time. Look at how fast that's moving. But this is why I did it while we're far out. You see how easy it is to change the moon? We just did a 90-degree inclination adjustment in just that little span of time. That was it. Not bad at all. I mean, we wasted a lot of fuel, but, I mean, no more than 200 or 300 meters per second. Okay, so here's what you're going to do now. We're now on the point where we can adjust our inclination. We want to get it as close to the base as we possibly can before we get down to it. So what you're going to want to do is you're going to want to go all the way in. What the heck happened? You're going to want to go all the way into the base, and you're going to want to adjust until you get where you want to get. So let's add just a little bit of orbital adjustment and see which way we go. That's the right direction. So I'm just going to keep tapping that. Wait for the solution to settle out. Okay, I'm going to tap it again. Wait for the solution to settle out. Okay, I'm going to tap it again. And wait. I'm going to tap it again. And that's it. Right there. Smack on. Okay. So that's all we can do for mid-course corrections. Oh, that wasn't the mid-course correction. That was the base target burn. Base target burn. Okay, so the next thing that I want to do is select a altitude to be at. I want to be a little bit lower than 180 kilometers. So we're going to perform a height adjustment, but we're between periapsis and apoapsis. So now what are we going to do? We're going to do something called burning outward. We're going to burn outward at 270 degrees. And what that's going to do is that's going to change our prograde velocity vector from here to about here without changing the magnitude. And what that's going to do is that's going to slow us down even more. So we're going to move to 270, which is towards the surface. And we're going to remove some radial velocity. You can't use a autopilot for this. You got to get really close because otherwise you're going to adjust your relative inclination, which I just spent a good time getting perfect. And it shouldn't take my... wow. Okay. I overshot. That's too low. So I'm moving to translation now. We're going to do a little bit of translation here to get us back to 100. Perfect.
Rotation.
Okay. So we're on rotation now. So now we're at F62 on the page. If you're watching the video, you're probably going to need to fast forward now a little bit to, let me see, F62. Should be visible at 5845 on the video. Okay, so we're going to use the Viz-Vifa equation to calculate the orbit entry delta V. So right now, we've got our mass of the moon, which is not going to change. So now we need R1. R1 is going to be where we do this. So now we need the radius of the moon. So I'm going to go to Info and hit Celestial Body. And look at that. It actually selected the moon for us. That's really handy. So I was off by 2 kilometers, not 1736. It's in fact 1738. So we're going to use 1838000 because we're using 100 kilometers in altitude. So add, 100 to 1738000. Okay. In F66, I'm going to add our semi-major axis, which is negative 7.431 times 10 to the 6th. Don't worry about what that means. That's a little bit advanced for understanding, right? What is our semi-major axis? It's halfway between apogee and perigee. But here's the problem. Our apoloon, as it's called for the moon, does not exist. There is no such thing. There's no such thing as an apoapsis right now. So don't worry about what it means. Our V1, we're going to have to figure out, let's see, when we get down to the surface... Oh, shoot, did I forget a equation to solve? Hang on a second. I'm an idiot. V1 is solved for us. That's the whole reason I had the equation. So right now we have 1006 meters per second. When we reach the lowest point of the orbit and swing around the moon, we're going to be at 2448 meters per second. So again, we're now at R2, which is going to be exactly the same, 1838000 into F68. Into F69, we're going to add the semi-major axis, which is also going to be, for a circular orbit, 1838000. Okay. And our V2 is 1632. That's going to give us a delta V of 815 meters per second. We have 5,000 meters per second precisely left in the tank. That won't be a problem. Our main engine thrust is 320,000 newtons into F72. And in F73, we need our spacecraft mass. So again, go to info, and we now weigh 18,508 kilograms. So with a delta V of 815 meters per second, it means that we're going to be doing approximately a 47-second burn, which means we perform our burn to periapsis at 47.13 over 2, or 23.5 seconds, which is ironically 1,000 times closer to periapsis from now. When PET says 23.5, no value here, just 23.5, and that's it. We hit the engines, retrograde, and we pull our orbit into the moon. So with that, we have everything squared away. We are ready to approach the moon. And our inclination and other things will move just a bit. You know, see our periapsis altitudes changed a bit too. That's because the moon wasn't accounting for all of the what's the word I'm looking for? The moon wasn't counting for all of the gravity, but now we're up to 85%. So let's see. Now I'm going to do another adjustment. I'm going to do this adjustment. And I'm really getting punchy with the, to try and limit the length of the video. Really getting punchy with the time acceleration. Just a little bit. No use getting too close to 100 because it's been... Okay, quick save, and let's keep going. Okay, things seem to have settled in pretty close to now. I'm not seeing our periapsis altitude moving much. Okay, so I'm going to slow down to 10x, and what we're going to do is we're going to do the next equation, which is the base's longitude. The base's longitude is 33.4 west. So it's going to be negative 33.44. And we're going to do our burn longitude at negative 213. You can add the number if you want. Add 360 and you can get the other number. I'm going to do that now. So when our longitude is 146.56 east, that is when we're going to perform the base transfer burn, which hopefully will be somewhere around our periapsis. But we'll have to see. Okay, going back to 100x. And this is the moon now getting really big outside the window. Because the moon is airless, I like to use green as my HUD. Okay, here we go. The moon is really drawing us down now. The moon is accounting for 99% of the gravity field now, as you can see. Okay, we're about 10 minutes from our retrograde burn, and we should get our first good look of the moon. Let's see what we're at 171 west. It's going to be really close. I don't think we're going to be in a position to do it single burn, but that would be really interesting if we were. Okay. And keep an eye on that number. 400 seconds. .300 seconds, just less than that. .200 seconds. Okay, we're 100 seconds away from the burn. So, well, as it turns out, we're almost actually retrograde. All right, activating the Ret-G autopilot. We're actually so close to the moon now that you can begin to see the topography and relief. It's really bumpy compared with the Earth. Okay, because I adjusted our altitude just slightly, I'm actually going to redo the calculation. So this will be 1840,000, negative 7.402, negative 7.402 to the 6, and 1840000, 1840000. Try again. Okay, so, wow, not that much difference at all. Still 23.5 seconds. Again, there's nothing telling you when to do this, so you watch that time. 23.5. 6, 5, 4, 3, 2, 1, 0. We're removing 815 meters per second of delta V, and we've been captured by the moon. We're going to stick around here for some time. We're going to continue decreasing this, and we could do a base target burn, but to keep things simple, we're going to do one thing at a time. So we're going to continue burning until our delta V gets down to about 1632. We're almost there. We should get a circularize at about 1632. Hang on. Yeah, 1632. Oh, right there. Okay, we have a perfectly circular lunar orbit now. So again, I'm going to quick save. Disable the retrograde autopilot, and we have ourselves a moon. Isn't that really cool? So that's from 100 kilometers. We're going to roll forward now until we're back to where we should be. Again, we're going to do this when our longitude is opposite our bases. So we're at, remember we identified 144 degrees east or something like, yeah, 146.56 east. That's going to be somewhere around here. So we're going to skip all the way around, And unfortunately, we'll be landing at night, which really sucks. This here is the far side of the moon, which you don't get to see very often. In fact, unless you're one of the Apollo, unless you're one of the 12 Apollo astronauts, 14, because Apollo 13 counts. Only 14. Wait a minute. Hang on. Three-man crew, 7 missions, 21. Unless you're one of the 21 people that crewed the Apollo missions, you have not seen the far side of the moon with your own eyes, ever. Okay, we're at a descending node, and I want to make a inclination adjustment, actually. So we're going to descend because we actually want our inclination to decrease. Again, we're just lining it up 100%. Actually, at this time, you know, we really should be changing our display to ground track, but ground track is going to look almost exactly the same because the moon rotates so slow. Yeah, that's our ground track. See how sandwiched those are? That's how slow the moon is rotating. Wait a minute, I'm getting this wrong again. This retrograde stuff can really trip you up. Notice because we're so close to the moon, it's not quite as easy as it used to be. Okay, let's try that. Let the solution compute itself. We're going to do one more quick one. Let the solution compute itself, and right there. That's good. Alright, so we're going to disable orbit, go back. Alright, now we're really going forward to when I said we were. Base transfer burn. Okay, so I did a radio check real quick with Brighton Beach. That right there, those lights, that cluster of lights, are the 6 pads at Brighton Beach. So if you go to select COM nav and adjust nav 1 to 116.30 for the VOR and pad 2 because pad 1 is full, 132.30, that'll get the pad. Now if you go to select VOR VTOL, you will actually be able to pick up the radio signal if you're within 500 kilometers because the VOR is very strong. So that's about it, and we're coming back in just about 1 orbit from now. Okay, we're getting really close. We're also in the lunar sunrise, which is pretty cool. So now it's time to turn retrograde. This part's cool because you get all sorts of like little crater shadowing and whatnot, which is a lot more possible. The lighting looks a lot better now that the moon is 3D. I have to say that's the one strong point and selling point of Orbiter 2016 is the 3D-ness of it. I could care less about the Earth because it's got hardly any relief, but when you get in a body like an asteroid or something like the moon, heck yeah, it matters. Okay, so it doesn't have to be exact. This really doesn't need to be exact. But we're going to do a base transfer burn at 146.56, and we're going to burn till our paraloon goes down. Hey, our apoloon is there. We're going to burn down to our paraloon is at 24 kilometers. I'm not going below 24 because we could smack into something. 146.5, here we are. Ooh, jeez, Jesus. Forgot we're on the moon. So strong. So strong. We're so overpowered. Our engines are extremely overpowered. Totally forgot about that. Now we're going to get really low. Like some of the mountains on the moon are 12 kilometers. So it's kind of almost going to be looking like you're in a Cessna going over stuff. So at this point, we're going to turn our lights on. I think everything else is good. Still got 4,000 meters per second delta V capability, which is where we want it to be. We're going to open our retro doors. We're going to need them. We're going to use the heck out of them.
Nose cone open.
No, the nose cone is not open. Not open. Okay. Save again. Okay. So now we need to do some extremely important stuff, right? This is the vis-viva equation stuff. So we know that our minimum altitude is going to be about 24 kilometers. So let's see, our R1, it doesn't look like I built this equation. So our R1 is going to be right there, 1763,000. Our A1, again, make sure you don't use altitude, you use radius values. 1803,000. And so we get a delta V of 1,685 meters per second. We have a main engine thrust of 320,000 newtons. And let's check our mass one more time. Do a mass update. Our current mass is 18,056. Round up always. Our delta V is 1685. That gives us a time to burn of 95 seconds and a distance to stop of 80 kilometers. So when we're 80 kilometers from the base, that's when we hit the brakes. But I'm not done yet. We have to calculate the potential energy. The mass does not change. Let me check on the G value to make sure we're using the proper altitude and 1736. No, that's incorrect. Change F93 to read 1738,000. That's the squared term. You should get about 1.62 Gs. Our H is going to be a lot lower. It's going to be about 24,600. That's going to give us a total velocity of 282.5 meters per second after we fall. Given the G value of 1.62, our hover engine thrust, now I have to look up this parameter. We're going to go into do info again, and we want focus vessel. Our hover thrust is 182,500. 182,500 newtons. That is an F99. So fill that out, F99. Spacecraft mass is going to be the only place that we can't estimate. We're going to get a burn that's about 95 seconds long. I forget what our fuel flow is when we're full, but it's probably somewhere in the form of 20 meters per second. But I can tell you, if you up-estimate, you're safer. So in F100, let's add 18,000. We'll have to update that in real time, but it should be okay. At a velocity of 282.5 in F101, we'll get a deceleration of 10.13 meters per second squared. When you have to combine it with the moon in F103, it means it's going to take us 33 seconds to slow down. And when it all comes together, it means that we need to begin our deceleration no closer than 5 kilometers from the surface at F104. Starfighter, end of the thing. So we've got everything we have now. So this is it. We're going to go over to VOR VTOL, and we're going to go until we get a signal. I'm also going to disable Ret G. All right, guys, this is really important. One thing that I want to mention that's new in Orbiter 2016, the moon is really hilly. If you want to land on something that's really close to the top of the moon, you cannot and you should not factor in those hover calculations that I said, 4686 above the surface, because, oh thank goodness, this is radio. Look at how this altitude is changing. We're going over the hills on the moon, up and down, so that's changing. And you got to factor in when you start making those distance calculations, like that I said, we need 4686 meters per second to stop. You better pick this one, because if you don't, you're really going to be asking for it. You won't make it to the surface if you're on a really hilly area. Now, as it turns out, Brighton Beach is named for a reason. It's basically at the surface of the moon, so that's why it's called the beach. So one thing that I want to do right now, okay, we've just had acquisition with Lima Bravo Bravo. So what I want to do now is a ad hoc change here. So this is going to have to be really fast. So we want to burn to the left. That's going to be out about...
rotation.
I left it on translation. So we're getting really close now. There we go. Much better. So what we're doing is we're steering the path. Don't think of it so much as up and down as it is left and right. We're steering ourselves to go directly over the base. Okay, now quickly turn retrograde. So we're at 344 kilometers. Again, the distance to stop is about 80 kilometers. So again, this gold arrow represents our distance, or sorry, it's the magnitude of our magnitude of our velocity vector, and the green cross is going to represent the location on the lunar surface of the base. So I canceled the Ret G. We're going to go to surface. You want to turn to surface now. And what you're going to do is you're going to line up the yellow or the gold arrow with the very back of the ship. And you got to stay on your toes, because this is where stuff gets real, okay? We told about all the mission critical stuff. This is where this comes up. As soon as we begin this process, we're on a collision course with the moon, and we can't finish until we either turn around or we stop. Okay, so we're pretty much lined up. Activate horizon level. Again, make sure that your retro doors are open. Make sure that all of your lights are on. And we are just about set. I need to get my numbers here. Your distance to stop, just about 80 kilometers. There are no retro doors on this craft, so we're okay there. Again, making sure it's right there. We're at 195 kilometers to go. 195 to go. $167 to go. And remember, 80 is the zero time. You can't go anything beyond 80. So it's better you burn before 80 than after 80. Okay, so if you can see, we're going to be going a little bit to the left. So what I'm going to do is I'm going to turn right to compensate. And if you look at that vector now, we're going to actually force it more towards the green. You want the yellow and the green to converge. Okay, we're getting really close. 107. This is the critical point where we're going to have to start adding hover thrust and whatnot. So it looks like the difference, we're at about 3 kilometers altitude. So again, don't look at this number here, because this represents the surface of the moon. 80 kilometers. Oh, crud. I think I missed the opportunity just a little bit. Okay. So in order to stop as fast as we can, I'm going to go straight in front of this vector. And we are stopping at maximum deceleration. Somewhere underneath of us, there it is the base is coming into view. Keep an eye on that altitude. It's going to start dropping. Kilometers to the base. "26 kilometers. Keep an eye on that altitude. Okay, so what we're going to do is we're going to stop alongside the base and we're going to add some velocity back into the equation. So here's what we're going to do. We're going to wait until the velocity bottoms out, right? We are moving towards the surface, which means we are picking up velocity. That is extremely important to remember. So we're getting really close, and right about there, we've just bottomed out. So now what I'm doing is I'm doing a high-speed rotation. We're going to put the vector of the base directly behind us, and I'm going to add retrograde, which is going to move the velocity vector backwards towards the base. Keep an eye on that altitude. Cannot reinforce that enough. So we're still about 6 kilometers away. So a reasonable horizontal speed might be about 60 or so. Should be above 60 meters per second. Test the hover engines. Okay, they lit. Good thing to test your hover engines before you finalize the landing sequence. I actually can't see the bait. Oh, there it is. It's actually almost under us. Okay, so we're getting really close to running out of fuel now, but that should be okay. Let's see, how far are we? We're about 4 kilometers from the base now. We're now below 10 kilometers altitude. We're getting really close. Getting really close to that range now. So I said 282 meters per second is where we're going to impact the surface. So we're getting pretty close now, and we're still at about 3 kilometers. So I think I'm going to go ahead and start adding stuff in now. So start pulling your hover speed down, and you can see we're coming into the base now. I'm going to try and swap over to nav 2. Okay, we can get the base now on nav 2. Okay, so at this time I'm going to reduce my hover thrust until we 0. Okay, as soon as our vertical speed gets down below about 40, there we go. Reducing hover thrust now. And what I'm going to do is I'm going to add some forward thrust. We're going to begin starting to cancel this this horizontal speed. We are almost directly over the base.
Translation.
Okay, I've now
1,000.
switched to translation, and I'm going to begin translating our information. Why is it saying 1,000? We should not be that low. Okay, so we're now translated, and now what we're going to do is I'm going to rotate to face forward the base again, and that will center us above pad 2.
300. 200.
This is really scaring me. So I had a good approach, and then the GPWS call-out started scaring me, because they essentially said I was 200 meters in altitude. That was extremely disturbing. Unless they're telling me my horizontal distance. See, now I'm going back down again. See, that would have been really good if the GPWS didn't scare me like that. I don't know what that was about.
400.
So we're almost directly above the pad now. We're going towards it.
300. 200.
So I'm going to keep the vertical speed down around 14. Actually, you know what? I think I'm just going to...
100.
Yeah, I'm going to get really close around this. I want to see what's going on here.
50. 40.
I haven't encountered this kind
30.
of thing before.
20.
And I'm a little bit worried that this is bugged out. So
10.
I'm going to be really careful. Did we touch? I actually heard us touch. Our altitude continues to decrease. Ugh. Orbiter 2016 is a mess. So we're still at 2.5 kilometers altitude, so there's no need we need to be this slow. I think about 20 meters per second is an acceptable speed for us. So just keep adding it in until you see that vertical speed stop moving. I do want to get out of the sky fairly quickly because we are kind of close to running out of fuel. That's about where we should be. We're coming down at a good clip now. So we've reached the end of our calculations. Everything else is just a visual approach now. The final step is to, well, actually, below 200 meters, we're going to put the gear down. Okay, we're coming up to it now. I'm adding retro. Adding retro.
Translation.
Okay, we're going translation again. So now what I'm doing, I'm using 6 key, and we're centering on the actual pad. That's it. Kill your horizontal speed now. Okay. Time for me to start accelerating again. So we're in final approach now with the pad. 1,000, because it's not doing. Okay, we're getting close now. Bring us down to about 10. 10 meters per second is a good place to be at now. Okay, we're getting really close now that you can hear that beeping. Okay, there's 500. Gonna bring it down to about 6 now. $400, we're coming down. Looks like we're drifting a bit, so I'm going to add just a little bit of translation to put us back towards where we should be going. Okay, 200, I'm going to go down to about 5 now. Landing gear's coming down.
Radiator deployed.
Okay, moving down to 4. We've got 3 lock lights. Moving down to 3. Moving down to 2 meters per second. Okay, moving down to 1. Okay, moving down to about a half. For this, I would say the HUD is the most useful thing to use because it's the only thing with enough, with a frame rate high enough for you to be able to tell what's going on. Okay, this is it, slowing to contact velocity, 0.2. Expecting touchdown any second. Well, this is extremely... what a wreck. Can't even see the surface. I like Orbiter 2010 better, even for the moon. Nice try, but even for the moon. Okay, we should be less than 1 meter from the surface. Watch that vertical speed. Okay, we have just touched. Remove all hover thrust, disable your horizon level, and tap the brakes. That's it. We've just come to a soft touchdown on the moon. Close your retro doors.
Nose cone closed.
Rotation.
Attitude off.
Disable RCS. I guess pitch must have slipped back on while I did my little fix. Turn our lights off now. And that's it. So here we are on the surface of the moon. It is a little bit unfortunate that it's night. You can't see anything. That really, really does stink. Because I can see there's a pretty big mountain out to this side over here. Interesting though how we like sunk through and now we've landed back onto the pad. I'm not sure exactly what happened there. But anyway, here we are settled on the surface. The radiator can stay open because it's night. And yeah, that's pretty much it. We're pretty much done here. So I hope this was useful for you guys. I know there were a few parts that were just like really irritating, like the approach and whatnot. There are MFDs that can help you through that. Or if you're a nerd like me, you can just do your calculations in advance, like using numerical solutions with aiming radii and whatnot, and then you can figure out exactly which angle corresponds with which inclination and whatnot. Do state vector manipulation, all that boring stuff. So yeah, that is it. Welcome to the moon. And I have to see what's next on our list of tutorials, but I hope you guys enjoyed this, and I will see you guys next time. Bye-bye. Oh, real quick. Brighton Beach faces the Earth. And there is the Earth, the sky. So that's how far we've come.